Muneeb, there's so much stuff happening in the world today, especially around AI. What do you see as the biggest shift over the last year or so?
Yeah. So we have really gone from the race to build more capacity, more power, to now really start to ask the question, what does the return on all of these investments look like? And that's essentially one of the bottlenecks as well, that we really need to start to see that with all this investment in this very important capability that we are building, and this capacity is going to drive the human progress forward for many next decades to come. But I think we really need to start looking at the return question on this investment as well.
So one of the things that people are talking about is the limited amount of power that's really available. And you say at Tensor Machines, people don't know that they're not getting full value from the power that they actually have. Tell me more.
Yeah. So given that we have the shortage in many resource capacity, from the chips to power to even cooling, at Tensor Machines, what we do is we are building the foundational models that can really understand the chip's health, chip's performance at its foundational physics layer, and then can estimate its aging and its degradation. A chip that's in the degradation state is going to use more power and produce less compute. And we are trying to put the operators ahead of that curve so they can use the power they have available most efficiently and can optimize their infrastructure for the longest of life and for the most productive hours.
It sounds like this is not just a PowerPoint of theoretical ideas. This is something that you have ready to go today. Can you tell us more about that?
Yeah, absolutely. We have two design partners. We are deployed across hundreds of GPUs. And what we are really doing is we are trying to understand the end of the life cycle for a lot of these GPUs and trying to understand their behavior at runtime and collect a lot of the physics, such as the thermodynamics and power dynamics, to really start to understand under different loads, how does the fundamental truths about these chips change and how we can utilize them to drive more efficiency and to enable the maximum productive life of the GPUs.
It sounds like there is the ability to take a snapshot of things, of the state of these things today, but there's not really a full life cycle management of how to optimize this. Is that an accurate depiction?
Yeah, that's correct. So a lot of these data centers are very well instrumented, and we have a lot of innovative solutions coming up when it comes to further instrumenting them. But really, what do you do with all of this data, and how do you interpret it? And I think as we are moving from more software-centric to hardware-centric, as hardware has become a bottleneck, we really need to develop hardware native solutions. So what we have done here is that we take the data and the physics informed neural network that we have, take a physics first look at a lot of this data to start to then really map out the life cycle that physically at its transistor level, how the GPU has degraded, and then can perform corrective actions.
Interesting. So going down to build a foundational model based on the physics of the devices themselves, what do you see that's out there today? What are people using today to model these things?
Yeah. So as I talked about, that we are going from 2 or 3 decades of building software and optimizing software to now really, as these models are becoming more and more widely used, the software is becoming more commoditized, and really the bottleneck's gonna be on the AI infrastructure side, and especially the hardware. So what we see out there today is really the solutions and the dashboards and observability portals from the software world being juxtaposed onto the hardware infrastructure. So you can see like dashboards that can report some telemetry, but then there is a lot of latent information that's hidden underneath the sensor streams, where we really need to take a physics first approach to understand what's been happening.
Great. And how do you bring that into action?
Yeah, so we have a model that is physics informed. So we take a lot of the sensor streams, we start to map the thermodynamics and power dynamics, and those start to predict the degradation. And as we start to understand the degradation, we can perform multiple corrective actions. One can be at a lower layer, we can adjust the cooling, we can adjust the voltage, we can also do dynamic workload placement on the chip. So most important workloads go on the healthiest of chips, but also we start to understand based on the operational playbook for these infrastructure providers that if something needs to be derated or maybe resold into the secondary market. So it is also can be a pipeline and a trust mechanism on how we build a secondary market around these very important GPU components.
So these models and algorithms sound extremely powerful. How do you insert this powerful knowledge into an existing data center or with an operator? Do you need to open up machines and get into them? How do you go about doing that?
Yes, we are not intrusive. We do not require a retrofit. We integrate with on-chip sensors and we integrate with BMC, so all the sensors that are available in the server. And integrating at these two layers, we collect as much telemetry that's already available to our data center. And we are able to build a deep topology of what's happening on the power side of things and thermal side of things. And then our neural network does the prediction looking at these two paradigms to understand how the operational aging and the degradation of the chip is going to happen, and can then suggest a list of actions that can be taken to improve the yield from those chips.
Now, Tensor Machines is in pilots already, and so you're collecting lots of valuable information on how to build these models, train the models. So what have you learned from these pilots that you've done?
Yeah, one thing that I can say that the life of a chip is not calendar based. It's really condition based. So it depends on the historical record of how a GPU has been used and also currently what kind of workload that is being placed on it and how the thermal history and its power history and the ambient environment has impacted its degradation. So even you can have two chips with the same calendar life, the same model, they can have very different actual operational age or operational life available because of the different operational history. And this is the latent paradigm and the latent patterns that I've been talking about that we have built models to expose.
And no one really has this today. This is a really new concept that you're bringing to the industry.
Yes, absolutely. We have 3 provisional patents across 88 claims where we have deeply studied the GPUs where we are already deployed upon, and we have collected a lot of data to really start to validate a lot of the modeling we have done.
So these are extremely powerful tools that you're now putting in the hands of operators. Surely they must need to change what they're doing.
They have better observability, and at the same time, they can perform corrective actions that are days and weeks ahead before the actual failure occurs. So what it means for them, less failures, less SLA credits that they have to give out. They will have more hours per GPU available that they can sell out to the model providers or their customers. And also, if you look at the peripheral industries around the GPU, which is the secondary market that's coming up, we'll be able to build trust depending on the condition of the GPU, that what its real value is, what its real pricing is, and bring more standardization to the secondary market. And at the same time, a lot of the financing and a lot of the insurance in the new AI infrastructure build out requires better risk modeling for the residual value on the collateral. And we'll be able to provide that underwriting layer for a lot of the insurance providers, a lot of the creditors that are building the financial infrastructure for the GPUs to drive their risk models more intelligently.
Given everything that's happening in the AI world today, why is this so important now?
Because as the models, they'll keep on growing larger and larger. There is definitely a place for newer chip architectures, for the frontier labs, for newer model training. But also, if you look at the nature of the demand from AI infrastructure, it's changed. There is a heavy emphasis on inference workloads. And for that, we really need to understand what supply of chips do we have right now that can take care of that demand. We are in the supply side constraint. There is memory shortage. There is shortage of packaging. And what we really need is to really understand how we can get the most amount of compute, the most yield from the infrastructure we have available right now. Also, as we invest more in the AI infrastructure, it comes back to the return. And for that, we again need to understand how productive our current AI infrastructure is. So in order to provide more productivity from the AI infrastructure, in order to get the most amount of compute and really enable the maximum productive life of this very important capacity that we are building, we really need to start to go towards the understanding of this AI infrastructure at its fundamental layer, which is, again, the physics-informed neural network that we are building.
As Tensor Machines is just getting started, what's the long-term vision for the company?
Yeah. So AI infrastructure, today we see it in data centers, but tomorrow we are going to see it everywhere. There are going to be sensing systems, there are going to be compute chips in the satellites, in the space, at edge, helping our defense infrastructure, helping our manufacturing industry. And for this distributed at-edge AI infrastructure, we'll need a control layer that can manage it, that can ensure that we get the most amount of compute reliably from these chips that we are building. And Tensor Machine wants to be that autonomous control layer deployed across this very important capacity, managing it, enabling the maximum productive life from these chips that we have in our economy.
Awesome. Muneeb, that was great. Thanks so much for your time today. Great talking to you, and have a great rest of the show.
Thank you very much for having me, Mark. Thank you.